Good afternoon, everyone. Welcome to DAT405. We're going to be diving into Amazon Aurora today and its innovations. How many people know that it's the 10th anniversary of Amazon Aurora? Yeah, it's been quite the journey since we pitched it almost like 13 years ago, helping to build it. So today we're going to dive in and look at the technology and how it can help you, hopefully, with your database needs. So what is Amazon Aurora? Well, it's a purpose-built cloud-native database. So it's fully MySQL and fully Postgres compatible separately, not all at the same time, because that would be odd. And we've built a lot of really enterprise-level features into it that go really great with the open source software that you come and love in the MySQL and Postgres space. So it has all these great features. I'm not going to walk through each one of them because you've probably seen this slide before, but it does have great performance, scalability, availability, durability. It's obviously secure, and it's fully managed like the rest of the RDS universe. But let's dive into the architecture. So what makes Aurora different? Well, the first thing is the storage. So I'm showing here one region with 3 availability zones. And that blue box is when you create a cluster, you get this volume of storage, right? And those yellow boxes are what we think of as storage servers. Now I'm showing 9 there, but in a typical region there could be thousands or tens of thousands of these. So once you have that, you can have a database instance, and the first one's going to be your read-write database instance. And that's what your applications are most normally going to connect to. And this is one where the first major differences from a regular database is we only write log records. And in this case, I'm showing 6 writes, and each of those is to a different chunk or segment, and those are 10 gig chunks. And they're spread across 2 in each availability zone. And we need 4 of 6 of these to complete before we're going to act the log write back, and you get your commit message as a customer, right? So that's how we get the durability in region. Now, the other thing that we do that is kind of different is we don't do checkpoints. We don't do full page writes in Postgres. We don't do a double write buffer in MySQL. And we don't have to archive any logs because we're not doing any backups up at the read-write node. So this means less work for it, more efficiency, more scalability, especially when it comes to writing. So all good things. But we read blocks, and I'll get into how that works in a bit. But this makes it really simple for the database to understand because we didn't have to change any of that. Now, we're typically going to read from the local AZ. There's a copy in each one. So we're going to read from the closest one because that's going to be fastest. And we don't have to do any quorum reads because we know from the basically sequence number where we are, and we know that we have the latest copy. So we read those blocks, pretty normal, right? What happens if we have a problem? Well, we can do repair if we missed a write. So in this case, we'll do a repair of that missed write from another one of the chunks in the same or another availability zone. So all this repairs and checking is all happening behind the scenes. You don't have to do anything. If a whole storage server fails, same thing. We're going to replicate that chunk from another copy and put it into a new storage server. So this happens all automatically. Now, another fundamental difference with Aurora is if you normally wanted a read replica in Postgres or MySQL, you'd have to have another volume in EBS, and you'd have to spin up a database. Here, we get to use the clustered storage, and we just attach to it. But to keep our memory in sync, what we do is we send these invalidation or update messages across from the read-write node to the read-only node. Now, these are asynchronous, so that means there is a bit of lag. You might see like 30 milliseconds in some cases difference on those things, but it's usually pretty quick. And you can have up to 15 of these read-only nodes. And you can mix and match where you want them, which AZs, and you can actually choose which types they are. So I'm showing Graviton on the one side, Intel in the middle, and serverless on the far side. So you don't have to pick just one type and one size. You can pick all kinds of different combinations. And the storage grows and shrinks as you need it, and you're only paying for what you use. So this is, again, a fundamental difference from most file system-based databases where you actually have to kind of allocate a whole bunch of space up front. So that's kind of nice. In the case of a failure, what we're going to do is we're going to fail over to one of the read-only nodes in a different AZ, typically. And your application needs to know where the new writer is. Normally, it would it would look at the CNAME for that database, and it would resolve that via Route 53, and you're going to get that update. That takes a little time to propagate. So instead, what we've done is we actually have a whole bunch of different wrappers that allow you to integrate with both JDBC. I think there's Node.js and Python today for both MySQL and Postgres, as well as an ODBC one for MySQL. And these wrappers know where the writer is, so you don't have to wait for that DNS propagation. It means faster failover, less outage time. So that's a really nice thing that a lot of our customers are using now. So with these features, we get to be able to innovate in different ways. And one of them is local write forwarding. So here I'm showing a simplified version of that region. And I have a read-write application and a read-only application running. But at some point, we'd really like to scale, and we don't want to have to recode everything. So making that application read-only is tough. Of course, if we want to make it read-write, the challenge is it's not going to be able to write because that's a read-only node, right? I mean, hence the name. But what we can do is we can enable local write forwarding. And now this is available for both MySQL and Postgres now. We just released the Postgres version. And now you can actually write to that instance, and it's going to forward that write back to the read-write node. So it's not multi-writer. And then that write is going to get replicated back, and you're going to be able to see it. Now, the thing that is important here is what the visibility of that is. So we have a lot of different settings. So I ran this little just test where I do an update, a select, and a select. And you can see the times on the writer are 2 milliseconds for the update and like a ½ millisecond for the selects, right? The default visibility mode is session. And what we're going to do is when we do that update, it's going to take about 3 milliseconds. So it's going to take a little longer than it would on the writer because it has to be forwarded, and in this case, across an AZ, right? So that takes like a ½ millisecond at least extra. But you'll notice that this first select took 30 milliseconds. And the reason for that is that we actually have to wait for our write to get back to us and be replicated because we want to read our writes. And that's what the session level visibility is giving you. You get to read your own writes. But the next select is very fast, right? And the reason for that is because we haven't made any changes. So reading our writes, we know we're up to date, right? So that's good. Now, we have a kind of more fun mode, which is the eventual consistency mode, because that's sort of the performance no seatbelt mode, if you want to kind of make an analogy, where the update is the same speed, but you notice that first select is just the normal speed, and that's because you're not going to see your writes. You're not going to wait for them. And if you're not reading the thing you just wrote, fine. If you are, that's probably not going to be good for your data, right? So you can use this one, but you have to be very careful. And then the other one that's kind of interesting for some use cases is the global consistency. And here what you'll notice is that all my times for all my operations are the same. And that's because what's happening is every time I execute a statement, we're waiting until the time that we started that statement, like at time t. We have to wait for all the data that's been changed since t to be replicated back to us. So you're going to see complete global visibility of everything. Now, I wouldn't recommend doing a ton of this, right? Because you're going to be at the mercy of the replication. But if there's some things where you're just like, I absolutely have to know the right answer to the question, global is kind of interesting. And these are session settable. So you can switch back and forth in the middle of a session. So you have a lot of control here to use these. So this is a really nice feature. And those are the versions that it's available for. Now, we have a really nice feature that we get from this storage system, and it's called Global Database. So we have our region A. We'd like to have some kind of DR. So what we can do is we can just create a secondary database cluster. And what we're going to set up is storage, another volume in that region. And behind the scenes, that replication and server agent, you don't actually have to manage those. Those are all just hidden. And those are going to help replicate the data between these two things. But you'll notice that we don't have any instances. We don't need that because this is storage-based replication. So when we do our writes, they're going to flow through. Now, remember those chunks that I talked about, those 10 gig chunks? The nice thing about that means that we can replicate in parallel. We don't have to do a single stream, so we're not bottlenecked by a single stream. So when you have a high write workload, we can still handle it. So write comes in, it gets replicated out to sort of the normal places, plus the replication server, which then goes to the agent, which then goes to storage, and at that point, you're good, right? From your boss's perspective, you have DR. Now, it's probably going to take a while to spin up, and I have a whole nother talk on that, but this is, the basic setup. But you can add read-only nodes, and you can have one or many, and the replication agent is now going to update those read-only nodes just like they do in regions, so you can use them for reading. And of course, you can have multiples of them, and you can have your application over there doing read-only, and that write forwarding I talked about, you can also do it here. So the storage can also do repair itself directly, so it can actually send changes directly over if one of them gets lost, so we don't have to worry about any network kind of issues. So this is a nice setup, right? But sometimes it's challenging because you have to have your application know which region is the primary. So we've just introduced global endpoint for a global database. So in each region, you have a CNAME for your cluster. That's how you resolve it. And they're different. And you can see here the subdomains are actually like, they'd actually be a real region name, but just for this are region A and region B, right? And that means you'd have to make changes to your application if you want to switch from one region to another, which is kind of painful during an emergency, right? So we've introduced this global one. And to really make sure you knew it was global, we put the name in twice, which I really liked when I saw that. I was like, OK. And partially it's because the name needs to have it, but it also needs to be in a different subdomain. But that was just nice for the feature. So how this works is Route 53 is doing the resolution. So right now, region A is primary. So when you do a resolution of that name, it's going to point to the C name in region A. And in the case of us doing a switchover, where we're going to switch from one region to the other, we're going to do all the normal things for switchover, which is to verify that everything's OK, and then we're going to switch. Once we've done that, we're all up and running, read-write node in region B. So now if you ask that same resolution, it's going to point to region B. So you don't have to do anything. And this is actually done with some really cool technology, so we don't actually have to use the Route 53 control plane. So this is super highly available, this switching. Now, you're good, but guess what? We got to go back and set up region A. We do that automatically for you at the end of a switchover. And in the case of, everything's replicating normally, but let's say now there's a problem in region B, you can do a failover if you want. And that's the failover global cluster command with -- allow data loss. And this is because we want you to make sure that you know that there's going to be a difference, because during an emergency, these won't be synchronized because obviously region B is not available. So 2 different commands for how you switch or failover. We changed the naming a while back because I didn't like the original names. They were confusing. So this is my other talk that I gave with one of my colleagues on Monday, but hopefully it'll go up on YouTube soon, that covers more resiliency on the global basis if you're interested in that. That's DAT405. So let's dive into the internals of Aurora Storage. So what I'm showing here is the Aurora Storage node. Got a lot of different pieces. We'll walk through that. So we have a read-write instance like we showed before. And the thing I didn't have on this before is the storage daemon. We actually have this daemon that runs on the host. And this is what communicates from the engine down to the storage. So when we have a write come in, goes through the storage daemon, goes into this incoming queue. That incoming queue is in memory, so we can't act yet. We have to wait for it to move to the hot log. And then from the hot log, which is on disk, we can now move it, we can now act it back to the storage daemon and back to the engine, and your commit will come back, right? So we get another write come in, C. It comes into the incoming queue, goes to the hot log. Great, we get our act back. But we noticed that we missed B. So this is where our repair comes in. The peer node can actually send us the B change. And now that we have the complete sequence, we're going to go put this in the update queue, and we're going to merge it into the data block. So this is where we coalesce. So this is how we go from logs to blocks. And now when you go do a read, guess what? You're just reading a block back. So both those logs and the data blocks are backed up continuously from storage, so no load on the server, to S3 for both snapshot and point-in-time recovery. Now, the thing we've been changing a bit is we have a new I/O type that I'll cover in more detail, but as part of that, we wanted to start making some performance improvements. And so we do that on the I/O optimized storage SKU. And the first one we did originally was some changes to the storage daemon about how it behaves, how it batches. So this gets us improvements in latency, lower CPU, all goodness, right? But this is only really set up for when you're doing a lot of I/O, which is why we still have the difference between it and the standard I/O. Now, more recently, with Postgres 17, which is in preview, which I'll talk about a bit more, we're making some bigger changes. So what we've done is this now queue is no longer an incoming queue, it's a durable queue. So when a write comes in, write D coming in, comes to that durable queue, we can immediately act it back. And as you can imagine, there's less stuff that we have to do. So that means lower latency, which I'll show you, and less jitter. So all goodness. So this is a really nice improvement that we're going to be launching hopefully next year, but is in preview now. So let's talk about the Postgres updates that we've had over the last year. Support for Postgres 16 last January. We've just launched R7i and R8g support for families. We now allow our query plan management, that's our plan stability feature, to run on replicas. So replicas can have their stable plans too. I don't know why they didn't before, but now they do. We've done a lot of improvements for logical replication to really get the performance better, as well as caching. We've updated to a newer version of PG Vector for generative AI, and we've added support for a couple new Postgres extensions. And of course, as I was saying, Postgres 17 is in preview, which is really nice. Because one of the things about having it in preview means that we're very close to having it in production. So let's look sort of generationally at kind of the improvements that we've gotten with these new R7i and R8G. So this is a sysbench read-only workload. I kind of call this the CPU benchmark, right? Because you're not doing any writes, you're just reading cached data. So vertical axis is queries per second, you want it higher. So the blue line, or the green line is an R5 24XL. So this was the biggest box a number of years ago that we had, right? And now the new R7i 48XL, so twice as much memory, and guess what? We're now getting 2 times the scalability on reads. So anyone that says, hey, scalability on relational databases is dead, no. We're still getting bigger boxes, we're still getting more scale, it's great. But what's even better is the R7G, the Graviton instance is now available in a 48XL, and we get 2.7 times better performance, so almost 3x scale from where we were a number of years ago. So this is really nice. On the MySQL side, we've also been busy. We're up to 308, so that's 8039 compatibility. MySQL also gets the R7i and R8G support. As I mentioned, they have that advanced MySQL ODBC driver for faster switchovers. And we've done parallel export to S3 as well as enhanced bin log that I've talked about previously. So Aurora Serverless is kind of where we think the future is around some manageability to help you make running instances easier. So when I talk about serverless, it's what we call serverless v2 because I'm trying to stop saying v2 because we're slowly deprecating v1. And I'll get into why that's been a slow process, but we're getting there. So what are Aurora Serverless? It scales in place. So there's no switching, and it happens in seconds. So we can add CPU and memory second by second. You're charged on a second by second basis, and there's no impact when we're scaling up or down. So this is really seamless. So I'm just showing a Lambda connecting to an Amazon Aurora instance. That's sort of the high level. When you have an individual Lambda fire up, it's going to talk to your instance. Doesn't need a lot of RAM or memory. But as you add more Lambdas, use more memory, more CPU. And if you have some big reporting job come in, maybe it uses a lot, right? But then, guess what? We scale back down. So this really scales with your workload during the day or over the weeks or whatever. Now, one of the keys to this, like scalability of CPU is not that hard. Moving memory around is much more difficult. So I was very excited with the work the team did here on buffer pool resizing. So we monitor the buffer pool, and as reads come in, we know what's getting hot, what's not. We see the access frequency. So when more blocks need to be pulled in, we can actually expand the buffer pool, make room for more blocks. And this happens automatically, so you don't have to worry about setting how big your instance is to make sure you're cached, right? Every time you get more space. Now, if you stop accessing data for a while, guess what? We're going to evict those pages, and we're going to shrink that memory. So now you're back to a smaller footprint, right? Lower cost. So this is actually probably one of the most impressive things, I think, with our serverless offering. So one of the missing things for serverless v2 over serverless v1 was it didn't have scale to 0. Now we have scale to 0 on serverless v2. To demonstrate that, I was running a nice workload here. Sorry about the busy lines. It was a little crazy with the colors. But you can see I'm running a workload, and the blue line is connections. So here my connections go to 0. I stop my benchmark running. And then I've got my timeout set to 5 minutes, which is the minimum for scale to 0. So about like 5 and a bit minutes later, we go down to 0 ECUs, right? So it's parked, essentially. And then a few minutes later, guess what? I start my benchmark back up again, and we scale up. Now, the thing to note is when you scale back up, you're starting from 0.5 ACUs. So it did take like a couple of minutes to get back to 4 ACUs. But from a testing perspective, this is probably fine, right? Now, you will notice here I went to 0 connections, but it wasn't for 5 minutes, right? It was just for a couple of minutes. So this is configurable. So if you think 10 minutes or 20 minutes is the right time, because guess what? When you scale to 0, your cache goes away, right? So if you're actively doing something, you don't want your cache to go away, you might set that to a longer time. If you're more worried about cost, set it to 5 minutes. The other one that we needed to do was to scale larger. We now scale to 256 ACUs, so double the amount of memory and CPU. So I'm showing a configuration with 64 min ACU, max 128. The orange line is CPU. So I see a spike here. I was running at 70%. I'm going up to 100. I hit 128 ACUs. This is bad, right? My performance is not great. So I run the command, set max to 256, And we start scaling, and we scaled up, and in this case, my workload pushed us up to about 215 ACUs. That took a few minutes, but you can now do this online. It's not a big deal, and so that capability is available. And the last, hopefully missing feature was the support of our data API. So I'm showing that same Lambda, talking to Aurora. It seems simple, but you have to load drivers into Lambda to talk to your database, right? That was kind of painful. You have to manage your connections, because if too many Lambdas fire up, you could overrun your database. So the load and everything had to be handled. Now you can just enable the HTTP endpoint, and we're going to put that data API in and allow you to do HTTP connections, and then we're going to manage the connection pooling for you to your database. And there's some configuration there that you can tweak, but in general, it just means it's a lot easier. So I think with this, hopefully these are the last features that differentiated sort of V1 from V2, and we can move on to just only calling it serverless. So we've been working a lot on manageability, and when I say patching here, I mean sort of upgrades of minor versions. There's a feature that we, I don't know, possibly named poorly, called zero downtime patching, because zero is a hard thing. But the intent of this was to mean no disruption. It didn't mean that there wasn't some blip, but no actual downtime. So we have our application connected to our Postgres database, and we're running version 16.3, right? So we want to upgrade to 16.4. What we're going to do is we're going to look for a pause point. So for about a second, what we're going to start doing is holding new transactions from coming in and waiting for ones to finish. If ones don't finish, we'll actually kill those transactions and move forward. But if you have short-running transactions, like less than a second, which hopefully you do, because that's generally good, this won't be a problem, right? So we have that pause point. After that, we basically, inside the instance, hand off all those connections to another process, which I've named the connection holder. It doesn't actually have a name. And at that point, we actually take the session state from the instance and move that out of the instance. And then we stop it, and we start a new one with 16.4, right? Then we rehydrate that session information, and we hand back the connections. Bingo. You're done, right? So how long do people think that's going to take? Well, it used to take quite a while. Now it takes a lot less. This is a benchmark I'm running. Again, sysbench read-write this time. It's on a 4XL, so decent-sized instance. We're doing, 35,000 QPS almost. So I end up doing that patch, and it's 3 seconds of 0 QPS, right? So we're done that minor version upgrade in 3 seconds. But the thing you'll notice is 0 connections were dropped because my transaction size is small. So all you would have seen is at the end of that 3 seconds is a spike in latency that would have reported as, hey, my one thing took 3.5 seconds to run, but then you're back to normal. And you can actually, you get that information, that line that you see at the bottom, that ends up in your event stream, so you know exactly how many connections and how long the thing took. So this will vary a little bit depending on your workload, but we've really worked to get this down, and we're going to try to get this even smaller next year. So I'm hoping for 1 second, so that's the goal. The other area for manageability around upgrades is blue-green deployments. So what do I mean by that? So this is for database blue-green deployments. If you had, for example, Aurora MySQL and you had a version 5.7 of MySQL and you wanted to go to 8.0, right? Well, that's kind of going to take a long downtime to do, so you want that to be quicker so you can do a blue-green deployment. You start by doing a create blue-green deployment as the command. And what that's going to do is create basically a green version and make the original one blue. And you can see that the target has the name of MySQL cluster green dash, some number. So this is how you can tell the difference apart, right? Now, you'll see it. You can do this with Aurora Postgres as well, so it doesn't not just MySQL. We support both of those. Now, you'll notice that the starting version is the same, right? So when we start, both of these are identical. But as part of the command, you can tell us that you want to do like a minor version or a major version upgrade, and we'll do that on your behalf. So those can be automated. If you're doing a schema change or a parameter change or some other manual change, you can use this as well. You just don't have to give us any changes that you want to do during it. So the first thing we do is we upgrade the database to 3.0 on the green side, right? So that's in preparation. But now we need to get these caught up. So we start replicating between them. So we catch those up. And once they're basically close, we make this available for you to do the switchover command. So you do the switchover command, and you see switchover in progress. And then we're going to verify they're in sync. We're going to stop all the writes. We're going to let the last replication traffic drain, and then we're actually going to do the switchover. And you'll see switchover complete, and at that point, you're on the new cluster, right? And you'll notice that the names have all changed. So your ARNs and stuff are all actually all rearranged, so all your automation still works. You didn't have to go in and monkey with any renaming or doing anything. So this is, I mean, you could do all this yourself, but it's many, many steps, right? So this is just automating a whole bunch of things that were possible just to make it easier, right? Now, once this is done, you can delete your blue-green deployment. This does not delete any clusters. All it does is disassociate the two things, and this is because you may want to do customer verification because let's say a plan has changed on that MySQL. Like that would never happen when you made your version upgrade, so I don't even know why you do this, but assuming it might, you still want to do that. Once you're done and you've made sure everything's working, you can just delete that original cluster and you're back to just your normal setup. So we're adding more and more support for blue-green with other things, so you know, if it's not working today, tell us the feedback, love to hear it, but it's definitely something we want to do. Postgres does have some restrictions because this uses logical replication. You can't do DDL during this, you can't have lobs, and you are required to have primary keys and a few other things. But you know, if it works for you, it is really nice. The other area around manageability is Zero-ETL. And what Zero-ETL is a way to help you move data from Aurora, in this case, to Redshift. So normally you might use DMS, you might use a lot of different techniques. Now you can just you can add a Zero-ETL integration. And what this is going to do is set up a replication channel that's all managed by us that replicates your data, and you can select which tables you want into your Redshift cluster. And the cool thing about this is the lag is only 5 to 10 seconds once it's up and running. So you can actually build like real-time dashboards that are looking at your OLTP system, but running it from Redshift. That's like pretty powerful, right? Now, this is all automated, as I said. Like we do the initial seeding, we do the replication, we do all the monitoring. You can run analytics while this ingestion is running. And you have all the normal CloudWatch metrics you'd expect from Aurora and Redshift to be able to monitor this. But one of the cool features is you can actually put multiple databases into one Redshift cluster, right? So here I'm showing 2 MySQL ones, but guess what? You can put a Postgres one in. So isn't that kind of cool? Like you can be querying both of these things in Redshift that came from 2 different engines, which I think is kind of remarkable. And there's a whole ecosystem that we're building around Zero-ETL. I'm just talking about the ones here, but there's a lot of other things we're doing in that space. One of the nice things with Aurora, again being the storage layer, is we can actually do things more efficiently in this case. So at the storage layer, we're going to use parallel direct export, in this case for MySQL, to load that seed data. So that's going to mean a faster load for us over to Redshift. And then we're going to use enhanced bin log that I talked about earlier to do the CDC streaming directly from storage. So you're not doing this from that read-write node. You're not putting extra load on it. So this means the Zero-ETL isn't really affecting your primary use case of your OLTP system. And now you have good analytics in Redshift. If you want to see more, there's another talk that dives into more Zero-ETL, DAT405. Check that out. So I talked about the new storage types a little bit, IO optimized, but let's talk about why we introduced that. So let's go to our standard one. That's the original, the OG storage type, as it were. And I want to talk about why we thought we wanted to do something that was more predictable from pricing. And if you do a select from your application, it goes to cache. You don't pay anything for IO because it came from memory, right? But if you read a block, 8K or 16K, depending on MySQL or Postgres, you're going to pay that fraction of a penny, right? And if you do a write up to 4K in a log, it's the same price. Now notice that there's 6 copies, but you only pay for the one logical write. But if you wrote a smaller thing, let's say 1K, you still pay the same price. This is where the confusing part came in. If you write 4 1K log records instead of 1 4K one, you end up paying 4 times the price. So what this meant was as your workload changed, your costs changed. And so that if you're doing a lot of writing, this could affect your bill a lot, right? So that wasn't great, and we really wanted to fix that. So we delivered IO optimized, and this is really trying to get predictable pricing for all workloads, as well as improving the price performance for IO heavy ones. So it's just a selection in the console or in the CLI. You can pick either one, right? And it's at the cluster level. That's important. Like you don't get this on an instance basis because it's about the storage. You can switch back and forth once a month. So if you need to try it and you don't like it, or vice versa, you can do that. And this is typical where your I/O spend, if you look at your bill and you say, look, my I/O costs are more than 25%, then you should really check this out. We've had customers, like it says 40% there, but I've had some customers I talked to today, 70% savings on their Aurora bill that do a lot of I/O, right? And it's basically available on all the instance types. I'm not going to read all those. And you can get additional discounts if you're using reserved instances. And it's available on all the new versions, basically. So how does this look like in detail for pricing? The standard one is our normal on-demand for compute or RI. You pay as you go, basically, for storage and I/O, right? On I/O optimized, you're paying a premium on the compute and storage, but you're no longer paying anything on the I/O. And I know that looks like it's a big lift, but again, if you're spending a lot on your I/O costs, that relationship can be dominated by the I/O. So back to my same example, guess what? I don't have to walk through it all because they're all zeros, right? There's no cost. You're not paying for I/O anymore. But the other thing that we really wanted to do, as I said, is to have a mechanism to improve performance for heavy I/O customers. So that's what we've been doing with I/O optimized as well. These latest changes that I talked about with Postgres 17 with the durable queue, I want to demonstrate the performance. So this, I'm going to show you, this is HammerDB, so new orders per minute on the vertical axis, higher, better. These are all 16 extra larges, but there's some generational difference. So the first one in green is an R5, so an older generation. This is running version 12, so going away version of Postgres, and it's the standard I/O setup. So that's the curve we get. Not bad, we're still scaling, right? This is what happens if you go to the 6i, right? So slightly newer, slightly faster processor. Version 14, a little bit better version, but not a lot of performance difference. But I/O optimized. We saw a 1.9 times improvement in throughput on this benchmark by going to I/O optimized, essentially, right? So really nice gain. Now, if we go to the 7i, which is our newest version of Intel, still on version 16, so not with the newest changes, I/O optimized, we pick up another 10%. And then another 10% with these changes that we've done around the durable queue. So in total, what we're talking about is 2.3 times the scaling that we get now on throughput, just generationally from a few years ago, right? So that's like great improvement for someone that does a lot of writing. But as impressive as this is, the latency improvements are way more impressive to me, at least. So this is sysbench write only, so we're just doing writes. So the only measure is how good are writes. Latency on the vertical axis, so now we want to be lower is better. Green line is the 24XL, the R5, the largest we had at the time, and standard I/O, back when we had that, right, as the default. Now we have a 48XL, bigger version, 17 of Postgres with this I/O optimized, with the new durable queue. And what we see is a 3x improvement in latency at the low end and a 6.4 times improvement. And you can see that curve now on that bottom is very flat. Like we always scaled well. We could get more throughput, but you ate latency to do it. Now you don't have to make that trade-off, right? You're basically getting the best of both worlds. You get all the scale at low latency. So this is going to be a really nice improvement. We'll probably move it backwards, like it's starting in 17, but it'll probably be available in other versions later, but this is our first release candidate. So, and that of course translates into throughput. As you can see, with this lower latency, these larger systems, we're now up to a 5x improvement from previous generations on throughput that we're getting with write-only workloads. So if you do a lot of writing, this is a nice improvement. So what about reads? Well, we've been working on those as well. So we have a new feature called Optimized Reads. And one of the pieces of it is for temporary objects. So this is spill, like if you do a sort and you need too much for RAM, you spill it to disk. That would typically go to EBS, where we allocate twice the storage of memory, and you get read back. So it's all temporary, right? So this works okay, but we've introduced these new instance types, the Ds, so an R6GD and an R6ID, say that quickly 10 times. And these allow us to have NVMe storage on the system now. So instead of doing that spill to EBS, what we're going to do for standard I/O, we allocate 6 times the memory in NVMe that now you can spill to. So if you need more sort space, you can have it. You can also get increased speed. I should really fix this animation to make it faster. But now, for I/O optimized, we only allocate 2x of the memory size in the NVMe for temporary storage. So the question is what's going on there, right? What are we using the rest of it for? That's where we do a tiered cache. So why do we want a tiered cache? Because in Postgres, if you read a block, if it's in memory, shared buffers, it's just going to get read, no problem, right? Comes back, it's quick. But if it's not in cache, then it's going to have to come from storage. That's going to take longer, right? Now, this might be OK for your application, might not, especially if you read a lot. So this can slow things down. So now what we can do is we have the space for temporary objects. Now we have 4x the memory in the NVMe as a cache for blocks. We take a little bit of the RAM in shared buffers to use for metadata. But now when you do a read, it works fairly similarly, except for we check in the metadata to see if it's in the tiered cache. If it's not, then we're going to go read it from storage and put it into memory. Now notice we don't read through the cache, right? We don't change the read characteristics of the system at all. So at some point, you stop reading that block. You no longer need it, right? And it's going to age out of the system. So it's going to get cold. And you notice we now have a 1 over there to indicate that we have this block in the metadata. It's in tiered cache. So when we ask for the next read, it's going to say, yep, I've got it. And boom, it's in cache. It's very quick, right? So now it's both in memory and in cache, which is fine. But where most systems fail or have problems is when you do an update to these kind of things, because that gets expensive, right? But for us, because we don't have to checkpoint blocks, all we have to do is when we get an update is we just invalidate the metadata. We don't even have to update the cache. We just won't ever go look at it, right? So the next time it gets evicted, we'll get a new copy. That's it. So this works very well, and it's got some really good performance characteristics. I will say at the moment we use random eviction, so this works best if the working set size of your data fits in the tiered cache. We are going to work on other eviction strategies, but we haven't got there yet. So when you think about heat, you want to think about working set size. So if you have this table, it's got a whole bunch of orders from all different kinds of years. It's 800 gig, but probably only like the last couple years are frequently used, right? So maybe the working set size is 80 to 100 gig. On this inventory table, it's per airport code. And so each of them is going to have different heat. So this one might have more heat, right? So you kind of have to understand how much heat and whether you can fit into the tiered cache. So let's look at how this looks when you're running sort of a benchmark. So this is sysbench point, select, read only. And this is a uniform distribution for sysbench. So this is not the typical one, but it's going to read it's going to touch every block, right, over time. So 4 extra large. And the workload is 85 gig to start with. That's the blue line. So the vertical axis is the number of blocks that are happening at each latency there. So that first blue line, that's memory, right? So we're in memory, and everything's good. Our latency is great. So whether you're running regular or a tiered cache at this point, it's all coming from memory. You wouldn't even notice, right? Latency is great, 0.23 milliseconds on average. But let's say we quadruple the size of our working set, right? We got a lot more data now. We're at 340 gig, still touching everything, right? What we see now is that we get a lot more latency at that bottom end because some of this is coming from storage. And so our latency actually jumps up by quite a bit, 4x higher, right? This might be OK for your application, but it might not. And the typical solution for this would be to, guess what? Buy a much bigger box with a lot more RAM, right? Which sounds like a good deal for us, but in general, we're trying to help the customers out. So if you go even larger, you get the same thing happening, except for more and more doesn't fit in RAM, right? That's boxed by the RAM is getting smaller, and we're getting more stuff out on storage, right? And we're now 5.5 times higher. So at this point, you're probably going to notice this in your application, right? So now let's add the tiered cache. So what we see is that pink line. We see that second spike, and that's the NVMe. So we're seeing some stuff come from memory, and a whole bunch of stuff come from cache. Now, 340 gig fits in the tiered cache at this size of an instance, right? So nothing's coming from storage. So we're seeing only a slight increase in latency. So you can see that like 1.5, a lot of times your application will probably be fine with this, and you can handle 4 times the amount of data for only a slight increase in cost over the base instance class. Now, you will notice if I double that again, now I'm bigger than the working set size is bigger than the amount of tiered cache we have. I have less performance, right? I'm now getting in the sort of like 3x higher. But this is uniform, and uniform is not necessarily normal. Most people don't read all the data in their tables, right? If we look at a case where I run sysbench with a Pareto distribution where I'm only touching some of the blocks, right? I get much better performance out of tiered cache, and I can have a very large database, like 680 gig, where pretty much all of it is coming from either the shared buffers or the tiered cache. A little bit randomly here and there is going to come from storage, but I end up only at 1.4 times higher. Now, to give you a real use case, we ran some of our PG vector tests with tiered cache, and what we saw was by enabling that, we got up to 9x reduction in time to do some of this vector work. So this can really pay off by not having to either buy a bigger box or wait as long. So definitely if you do a lot of reading, this is a feature to check out. Now the other feature that we announced last year at reInvent and GA just before this reInvent, just before, is our Aurora Limitless database. So what is Limitless database all about? Well, a lot of folks know that to scale out, a lot of times you need to use sharding, right? And that is something I agree with. You start with one database, and over time, as your usage grows, you do sharding, and you start splitting into multiple shards. But guess what? Like, as you get a lot of shards, that's a lot of stuff, right? And so for me, really, scale means managed sharding, and that's what we're doing with Limitless database. We're trying to make sharding easy. So one of the challenges, resharding. So if you have an instance, and you do the initial sharding, and you think, 4 sounds good, because why would pick a number be wrong, right? So that works for a while, but guess what? Like, you get a hotspot in that data. You got one bigger customer. They end up using up a lot of space, right? Now you've got a problem. Guess what? Now you're back to resharding again. So this is going to be a constant thing over time, right, if you keep growing the data. The other one is consistency. So sharding is nice, but let's say you want to add a column. Now you got to add a column to 4 databases, right? And you got to make sure your application's okay with the timing on that. And what happens if you miss one, right? Like, that would be bad. With 4, it's not bad, but you can imagine if you had 100 of these, that would be much more challenging. If you want to query, what are the open orders right now? Those are going to run at all slightly different times, right? If you try to do a backup, again, all at slightly different times. So if someone says, give me a restore as of midnight, you'll be like, well, I can give you a restore at sort of midnight. It's not really the same answer, right, that you're used to. So that's not great. So with Limitless database, we're trying to solve these problems. And it's still in your normal Aurora cluster. And this slide's a little different because we've made some changes since we did preview. We've gotten rid of the regular instances in the cluster. And now you just have the Limitless shard group. So as part of the Limitless shard group, you have this thing called the distributed transaction router layer, which has multiple things in it. And that's what you connect to. So you have a CNAME for that, just like your normal CNAME for your cluster points you now to this router layer. And that's where we do, as it says, all the routing and the transactions. And then we have a data access shard layer. And this is where we store all the data. Makes sense, right? So we've been able to scale this to more than 2 million TPS. This is kind of an old number that we have. We do automated resharding. So like, if you have a hot shard, boom, we can reshard it, or you can do it yourself. You can just say, I want to split. We have serverless capacity. So we're using all the stuff all that technology you've seen with serverless, so that as these things grow and shrink during the day, you don't have to reshard them. They'll just grow and shrink. So unless they get bigger than 256 ACUs, we don't need to reshard, right? The other thing is we have consistent query DDLs and backups, right? So if you do a DDL, it's going to go to all the routers, but not just all the routers, to all the shards. So it's happening all at once in a nice distributed transaction, so you don't have to worry about inconsistencies from an application deployment perspective. All the backups are consistent. So if you say, I want a backup at midnight, restore that backup, all of them are from that case. If you had any distributed transactions, they're going to be perfectly how they were at the time of when the backup was taken. So how do we do this? Well, we do this with clocks. So as you may have seen with like some of the other stuff, we've gotten now much better clocks, and we're able to use clocks to get synchronization. So I start a transaction over here, and I'm selecting from a PG bench table for the Postgres folks. And I just selected one BID, right, to get the value. What happens is the router assigns a time when that statement comes in of T100. And then because of the snapshot technology, we can go run on the shard at T100. So we're using the visibility sort of back in time now to run that at that exact time. So we get the correct answer of 704. Over transaction 2, we're selecting from the same table, but a different BID, 801, we're doing this for updates. So we're locking, we have all the normal semantics. This one's going to run at 103, because that's what we get on the router, that's what it's going to run on the snapshot. We get an answer of 1 here. Let's do the update here. So we're updating that balance now from 1 to 1001, right? And we do the commit. So at this point, we need to talk to the shard. We set a commit point of T110, right? And then we have to wait for that to be durable, and we have to wait for that time to basically pass, which is usually a tiny bit of lag, and then it's committed. So that's all good. Now, if another transaction comes in and runs that query on that same BID, what we're going to see is it's going to get a time of 125, right? Which is after 110, so our answer is going to be correctly 1001, not 1. But over here on transaction 1, notice we never did our commit. We never ended our transaction, right? So we're still in the original transaction scope. So if we do this select, it's going to run at T100, right? So it's actually going to get the correct answer, which is 1, because its read visibility is supposed to be back in time. So we use this clock for not only these queries, but for how we do backups and everything else, and that's how we get the consistency. So it's a really nice system. And it solves a lot of the problems. And there's a nice talk from one of my colleagues, DAT420, that you can see more details, full talk on Limitless. Now, most of you probably didn't hear this announcement, right, that we announced a new memory of the Aurora family called Aurora DSQL that Matt nicely announced this morning for me, just so I could do this talk. No, just joking. This is why my talk is after his, so that we could talk about this. Now, like any family, there's a lot of similarities between them, which is why it's in the Aurora family, but there's also going to be differences. And what I wanted to do is, I don't have an hour to talk about this, and there's a whole session which I'll link to, but I wanted to give you guys kind of sort of a snapshot of how you might compare and contrast the sort of Aurora Postgres with Aurora DSQL, so you can kind of see some of the differences and trade-offs, because there are there's some definitely advantages, and there's some things that you need to think about. So on the left, I have Aurora Postgres, and I'm just going to refer to that as APG for now because it's too long to say, and DSQL on the other side. So you'll notice the first thing is it says Postgres compatible, not fully Postgres compatible for DSQL. And what that means is that you're going to still get the same answers. Like if you run the same query, it's got the same semantics, all those things as Postgres. It talks the Postgres dialect. It has the Postgres commands. But it doesn't necessarily have all the features. And it doesn't, we'll get into sort of the, how it does concurrency and some of the commit stuff. So there are some differences there. And that's by the nature because it's a distributed database, right? So we've made some trade-offs there. So if you need full Postgres compatibility, if you're picking up an application that runs on Postgres today, Aurora Postgres, APG, is probably going to be your better answer. But there's a lot of advantages to DSQL that we'll get to. So they're both disaggregated databases. They both have separation from their compute and storage, right? So this is a commonality of the family for Aurora. In this case, Aurora stores its logs and blocks together. DSQL has a separate log store. So if we have read-write from an application come in, now we have a container there for APG, right? And that could be a serverless instance, it could be a revision instance, it could be various sized, whatever. On DSQL, what you're getting is a firecracker container that's going to fire up when the connection comes in. So it really is serverless, like boom. It didn't exist before your connection, now it exists. So these are much smaller, more granular serverless. But both of them write logs to this log storage, and this log storage, again, is across the region, right? So it's durable across the region in HA8. So this is the same common pattern. So latency here is probably going to be similar. It's probably maybe a little higher for DSQL because it's got some other stuff it's doing for the distributed nature, but in general, very similar characteristics. Now, one of the things with Aurora Postgres is it's single writer. If you have another connection come in, another AZ, whatever, it's got to go to the read-write node because we only have one. So even with the write forwarding, it's still one writer. So, but you do have implicit, explicit locking, right? You can do select for update, you can just do an update, and you get locking on that row. That's not the same with DSQL. DSQL is a true multi-writer system. So we can write anywhere, like I'm showing a different AZ, but this could happen in the same AZ, it could happen in AZ3. It's true multi-writer, but it's optimistic concurrency control. So when you do your commit, so the first one wins, and the other one gets an error, right? So you can't lock rows. This also affects that the transaction size is limited. Currently in the preview, it's 10,000 rows and 5 minutes. So it changes the characteristics a bit. But it is true multi-writer. And so the scaling is different. You're no longer constrained to the scale of one instance, even as big and as good of scale as we're getting with Aurora Postgres. So we have read-only nodes, as we've talked about for APG. And those all have caches in them, right? So we have our shared buffers, and those exist. So this is why we have to do asynchronous invalidation between them, because we have to keep the caches in sync. So when we do a read, if we read from the read-only node, this would be the same from the read-write, we're going to read from the data from the cache if we can. If not, we'll go to the storage, right? This is fundamentally a little bit different on DSQL. There is no cache. There's a block store. There's blocks in each AZ. And when we do a read, we're going to read directly from storage every time. The advantage to this is that we don't have any cache coherency between these nodes, right? Because you don't have to worry. It's in the storage. But as you can imagine, doing that read from storage can take quite a while. So the team has built pushdown so that we've optimized how read works, so you're not making many round trips like you would in a classic database. So you actually get quite good read performance even though it's coming from storage. And of course, it's, it's NVMe storage, like it's very fast storage. So the other thing, of course, is that because we're doing async on Aurora Postgres, read-only, it's eventually consistent reads unless you've turned on the right forwarding and you're asking for consistency, versus in DSQL, because you're reading from storage, everything is consistent, right? So it's got a nice advantage there. Now, again, as you fire up more connections in DSQL, you just get more of these containers firing up, one for each of the connections, right? So in serverless, as we talked about, after 5 minutes, if I'm not using this instance anymore, it will go away, and it can come back, right? In DSQL, as soon as you're done those connections, boom, they're gone, right? So it really is, you're paying for the workload. That's it, right? So there's nothing running if you're not running something. Of course, the one other difference is this is in preview. So we're still going to want your feedback. So everything I'm saying here, take with quotes because it may change. We value your customer feedback, and we'll make changes as we go. Now, the other area that these are similar is that they both have a global presence. They can both support the global nature of most people's businesses. So Aurora Postgres is our normal, memory or volumes in both locations. And when we do a write, we're going to do that asynchronous both to the storage and to all the nodes, right? So this is an active-passive system. So you have to do failover between them. And that's the same as in region for Aurora, right? You're failing over from a read-write because there's only one writer. So the same thing is true with global database, right? But because it's async, you're getting region-level commit latency, right? You're not paying for a cross-region write. So that's an advantage, but you do have stuff like your active-passive. Now, conversely with DSQL, same again. You've got storage in both locations, and true multi-writer. So you can write in either region, either of the regions, multiple AZs. This is truly active-active, right? So if you need that capability, this is where it really shines. Now you notice that I say sync on commit. So this is that optimization that Matt talked about in his presentation, is that we're not doing every round trip on every write, every update. We're only doing this at the commit time. So that means you're paying across region, but only on that one thing. So your cross-region, your latency for commits is a cross-region one. So it's going to depend on how far apart your regions are. But like if you can imagine US West to US East, you might be, you're probably sub 100 milliseconds. If you're between the two East regions, you're probably very quick, right? So you can see how you can use this to build things where you really want an RPO of 0 across regions. So hopefully that's kind of a nice intro to this. That's the deep dive session 424. That was, the title had changed, so this is the updated title with DSQL. So you can check that out if you want more information and deep dive into more of it. And with that, I'll thank you. And please remember to fill out the session. I really do value the feedback. Thanks.